let's go ahead and start with just a quick refresher as to what you have to do. It's kind of a three-step process. And so we've done this one already, and it should have been in your notes. But let's kind of begin with it again, the parallel plate capacitor. Now, before we launch into it, be very careful about the way the problem is worded when it asks for you to come up with the capacitance of a parallel plate capacitor. It probably won't be like that. They're going to want to use this problem in such a way as to test your abilities to do other things at the same time. So one of the more likely questions, especially if it's the parallel plate capacitor, would be something like, what Gaussian surface would you use to determine the electric field between the plates? And I'm not sure how you would answer that, because there is two possible answers you could use, but one of them is better than the other, and we didn't do this one in class. So the one that you probably would have used is some surface that is, uniformly placed on either side of one of the plates. This is not a bad choice. There's potential for a better choice, but this is not a bad choice. The reason why this is okay is we at least have one surface that is located between the plates, which you have to have. If we're going to be calculating flux from this Gaussian surface, we need to have at least one of the surface in the area where the electric field is being measured. The problem with using this, and I'm projecting this two-dimensionally, I think you guys understand that we did a cylinder. Do you remember that? So this is still a cylinder with this region being the sides, top, and bottom, or vice versa. The problem is that we don't really care about the electric field out here. And for Gauss's law, that electric field is not cumbersome, but you'd have to make a pretty good argument for why it might be zero out there. And you'd probably have to do so in your argument. Another way to do it, another surface you could have chosen, is this one. And people do it all the time on the exam to much disappointment, actually. Come on. There's bound to be a person who will do this. And I say this knowing I've given the same question for years. And there's always somebody who draws their Gaussian surface like this. The problem with this, of course, is that this Gaussian surface is completely useless for our purposes here. It doesn't have any surface that's actually in the region that's interesting, and that's between the plates. The best choice is actually this one. We know the plates of the capacitor are made of two metals. There's no reason why you couldn't place this as your surface, because this gives you three surfaces that will have no flux. If we assume the top plate is the positive plate and the bottom plate's the negative plate, then we know our electric field is this way. And it should be clear just from that argument alone that there'll be no flux through the side component of the Gaussian surface. And the flux has to be zero here because the electric field inside the metal has to be zero. That leaves just one surface to which you'd have a Gaussian, any kind of flux, electric flux. So step number one, though, begins just before this. And I probably should have said this from the beginning because they don't always include this step. The first step is to deal with what the charge is on your plates. You have to find some reasonable thing to say about the charge on the plates. This may be given to you, or this might be something that you set, but you establish the charge on the plates. That's step one. Now, if they give it to you, if they say it's charge Q, use what they give you. If they don't give it to you, if you can, just put a symbol to represent the charge. But if you have to, use a charge density, but be able to calculate the charge. Those are your three options. Use what they give you. And that's very likely. If not, can you use a symbol for charge? And if all else fails, can you use charge density? But the whole point is to find some expression that you can use for charge. And that's going to be step one. Establish the charge that's on the plate. Step two is to determine the electric field due to that charge. This is going to be Gauss's law, most likely. And if the AP exam wants to exploit your ability to do Gauss's law, they will do it here in a capacitance problem. It's an easy place to do it. Meaning you wouldn't be able to assume what the electric field is in that region. You would have to prove it using Gauss's law. It really depends on how they word the problem, but if they need to work in Gauss's law somewhere in the question, and they're not doing it elsewhere, they could do it on a capacitor problem by requiring you to solve for the electric field between the plates in the region of space that matters. Y'all are leaning over to see something. I said it out loud. Do I need to say it out loud again? I will. Just ask. Besides that, you guys look kind of funny, all trying to sneak around each other's heads a little bit. It says, determine the E field due to that charge in the region between the plates. That's what I said out loud. Now, again, if the word determine is used, like it is here, you might be able to just say, well, I know that the electric field has got to be this between the plates. But if they don't, they use the word derive, especially derive using Gauss, then you have to start with but this is where it's going to happen. So if they have a capacitor problem where we're deriving capacitance, they're going to put Gauss's law here. They're going to make you do the step for Gauss's law. Now, this should give you an electric field that is some function relative to shape. Almost always. And we know what it should look like for our three shapes. So we have kind of some examples to draw from. And we know for the parallel plate, we expect our electric field to look like this. We know for the coaxial cable, which is going to be a line of charge, we're going to have some form of electric field that's proportional to from your distance from the center. And if it's a point charge or spherical, we'll have these. These are our basic three shapes, and we kind of expect to see that. They might give you something you have to use here, but this is what your expectation should be. However, it is plausible there is a fourth option, that they've come up with a shape or they've come up with a dielectric that's maybe more interesting, and you will have to perhaps do more work with Gauss's law. They have done that before. They've had a spherical charge that was not a uniform density. They've had a couple different things. This is unlikely. Very unlikely. When all that's done, there's a third step. Put the R here to make it more flexible. But you're going to have to find the electric potential. I've left off the negative sign here because the negative sign in this calculation won't matter. You're going to go in whatever direction they tell you, but you'll be able to determine the capacitance. The capacitance isn't positive or negative. It's going to be just a holistic value. So you can't have negative capacitance. So don't worry about whether the potential here is supposed to be positive or negative. But I will state that this is just a temporary step so that you can do capacitance equals the original charge divided by the potential. That's what you're trying to do. So you're trying to find an expression for the electric potential that can be plugged in to the equation for capacitance. That's your third step. Find this function and plug it in for V. So let's go back to doing the parallel plate. All three steps. Step number 1, establish the charge on the plates. I'm going to say the plates have area A, separation distance D, and they are connected by, they aren't. And they have a charge Q on this plate and negative Q on this plate. I'm just going to say that they gave us the charge on the plate. So step 1, establish the structure, get the charge on the plates. Then, step 2, derive an expression for the electric field between the plates. That can be broken up into multiple steps. One of them usually is what would you use for your Gaussian surface? I'm going to use this Gaussian surface. I'm looking at a cylinder. And my cylinder has a top of area A. I better not use A. How about, I'm just going to say area of cylinder. And height of cylinder. And we know that we're not going to have to integrate over the whole area because our area is going to be broken up into 3 sections. So Gauss's law, if you remember, says something like Q enclosed equals epsilon naught times the integral of E dot dA. We've done this shape before, except there's one difference. We're going to have 3 separate areas: the top, the sides, and the bottom. When you're doing this problem, which we've done before, we're just simplifying it a little bit to say we're going to have E dot dA for the top plus E dot dA for the sides plus E dot dA for the bottom. And we're trying to structure this so that we have things that we know are 0, and we think those will be 0 because the top portion of my surface is inside the metal, so it experiences no flux. The sides are in such a way that no electric field passes through them, and therefore the only portion of the flux that matters is the part of the flux that passes through the bottom. So that gives us Q enclosed equals epsilon naught, and that's going to be E, which we think is constant, times area of the top. Now, we need an expression for Q enclosed. That's how much charge is enclosed, and in this case, it's the amount of positive charge that's currently hanging out on the surface of the inner portion of the metal. Now, I don't know if you know how to come up with an expression for this, but I know there's probably a point sitting there waiting for it. It shouldn't be hard to realize what you have to do there. But if so, I would consider that sigma has got to be the charge density. That's got to be Q over A. And we're enclosing a smaller area. So Q enclosed divided by the area of your Gaussian surface has to be the same ratio. You guys following along so far? I mean, we've done this problem before, so I kind of feel like I can hurry us along. But I'm going to take this, use it here for Q enclosed. Yes, sir. So continue on, I get, area. Golly, I can't write it all today. Area over A times Q equals epsilon naught E times area. I've been writing out the word area to differentiate the area of the plate versus the area of the Gaussian surface, just to kind of make it easy to see which is which, but also to recognize that it cancels out. This gives us what we're looking for, which is an expression for the electric field based on the charge on the plates, which in this case is going to be Q over epsilon naught times A. Now, this shouldn't be a surprise because we expected it to be sigma over epsilon naught, and sigma is just our charge density. So this shouldn't be a surprise. And the reason why it's not got the 2 in the denominator is because if you remember when we did a charged sheet, we had to place the surface on both sides of our sheet to basically enclose the electric field that was on the outside. But we know the electric field out here is supposed to be 0. So we can choose any enclosed surface. This one makes more sense, as we know the charge has been pulled to the bottom of that plate. Either way, that's all the stuff that you have to do to get step 2 done. So you want the step to say determine, but you have to be prepared for the step to say derive. Now, in the last 5 years, they've asked this specific question twice. It's pretty high frequency. And in both years, they've had you draw in what you feel an appropriate Gaussian surface would be in order to do this. Yes, sir. I can't hear you.
If it said determine, would you just skip all the way down to sigma?
Determine, you could probably start from something like, I know the electric field from a charged sheet is this, and make a reasonable argument that this would become due to both plates, and then based on the fact that the charge on the plate is Q. You'd still have to show your work, but you wouldn't have to start from a first principle. Where derive, you have to start from a first principle. You have to start from a law. See the difference? Okay. So keep going. All right, because that was step 2. Step 3 now is to find what the electric potential is due to this charge and this electric field. So step 3 is relatively straightforward in almost every case, but is probably where you're going to have the most trouble, since many of you are still getting into the whole integral thing. But V equals the integral of E dot dx in this case. Makes the most sense. We're going in a linear direction. And you have to set the limits. In this case, setting one place, probably the starting plate. It's not necessarily 0, but you need a starting position. You'll understand why I mean it's not necessarily 0 when we do the next one. But the outer plate's going to be D away, no matter where you go and what direction you go. We're going to assume we're going to go in a direction that's going to provide us with a positive electric potential. And we're going to skip worrying about the sign. You sub in, now you may not know this, and for some of you, I know I'm being redundant, but whatever you solved for for your electric field earlier, you have to sub that in here for electric field. They want to know that. They're going to give you a point for that. So make it obvious, especially if you know that this is wrong. You want this point, you want them to know that you know what to do next. So that means showing them what to do next. Don't try and force your answer to be right because you know that what you're doing isn't going to lead to the right answer. They can read through that. Follow your procedure. They need to know that you understand your next job is to find the electric potential from the electric field you just found. Now this is a constant. So this just becomes Q over epsilon naught A and the integral of 0 to d of dx. Now, I don't want to go all the steps here, but this is now the integral of x to the 0 dx. Do I have to go that minimalist, or can you guys skip ahead a little bit? I do have to go that minimalist. So if there's nothing there, then it's x to the 0 power. You'll have to show the steps anyways, even if it's all just worth 1 point. It's a polynomial, so x to the 0 becomes x to the 1, and I divide by my new exponent, evaluated from 0 to d. I know it's been a long time since we've done this, but I was hoping that your calculus classes advanced you a little bit. And that just becomes d minus 0, which I have no intention of writing out. I intend to write that out. That's your electric potential. You're not done. The end of this step is to take this and plug it into the equation for capacitance. So C equals Q over V, or C equals Q times epsilon naught A over QD. If done correctly, any reference to the charge should disappear. Look, that's how you know you've done it right. If done correctly, any reference to the charge should disappear. That's how you know you've done it right. Your answer should be purely something based on the structure of the object. If it's not, you've done it wrong. And that's how you know. Now, this one we've done before. So this is a rehash of something you've seen already. We need to talk about the next one. So, any follow-up here? Can we go on to the next one? All right, we're going to do a coaxial cable. This example was on top, and the one on the bottom was on the bottom, and the sides were along the sides. And then when I do this, so coaxial cable, we'll start with a coaxial cable that has a, I don't know, I need to, let's say an outer radius, nope, that's not coaxial. An outer radius of B and an inner radius of A. We're going to make the inner radius a solid piece of wire. So a solid conductor. It won't change it if it's a hollow conductor. So something like that. Not sure it looks great, but that's what I'm going to use. So it's a coaxial cable. Does everybody understand what I mean by a coaxial cable? All right. So this is the outer shell. This is the inner core. Now, all coaxial cables have usually the outside is made of a mesh, so it's a flexible wire, but all you need is an outer cylinder and an inner cylinder, and you have a coaxial capacitor. So it's, two rolls of aluminum foil, with one having a smaller radius and the other one having a bigger radius, is a coaxial capacitor. The process for finding the capacitance of one of these is the same. We have to make a few assumptions though. Assumptions that I think are obvious, but I don't know. Like, let's say that the whole thing has length L. We can't necessarily see the length of it, but we need the whole thing to have some given length. We already have an inner radius and an outer radius. So the first thing we're going to do is establish the charge. And I'm going to say that the inner portion of this cable is the positive charged portion, and the outer part is the negatively charged portion. I guess there's no point putting the plus next to that because you can't see it anyways. So I'm going to say there's a charge Q spread out on the whole core on the inner wire, and then there's an outer charge of negative Q on the outer wire. So once we've established the charge on our capacitor, the next step is to use Gauss's law to derive a function or an expression for the electric field between the plates. This picture doesn't serve that need very well, but I'm not sure any picture will. So, because the one on the top and the over pictures here, the first one I'm going to try and draw this as best I can, but understand I have limits to what my capabilities are. There, does that look good? With this being 2A and this being B. So kind of a cutaway view of what the cable looks like. Is that good for you guys? And I want to also do, just so we have a little bit more consistency, there's the inner core and the outer core. And that way we have, you know, there. And again, this 2A and this B. We good? All right. Using Gauss's law, derive an expression for the electric field between the plates. I'm going to use a cylinder again, I think. And I'm going to use a cylinder that is placed concentric with the inner wire. So something like that. That has height H and is radius R. I have to have a Gaussian surface that is closed and bounded. It is enclosing a piece of the inner wire. So a similar way to draw that here in the middle. Something like that. Now we've done this before again. This is old news, but let's go ahead and go with it, all right? We have to derive an expression for the electric field. That's going to be based on using Gauss's law. Can't remember the last time they asked this, but it's been within the last 3 or 4 years. This is relatively recent. Not terrible here, though. We've done this already before. And so for all of you who struggled with it the first time, you're probably still going to struggle with it some, but at least should have some familiar struggle to it. Doesn't make it easier, but at least it makes it familiar. We're going to break this up into 3 surfaces. The integral for the top, plus the integral for the bottom, plus the integral for the sides. Where this surface here is the top, where the surface back here is the bottom, and then that surface around the outer edge of the can here is the sides. Yep. Yep,
Why did you do that?
because I felt like it.
That's whack. Okay.
Really, Oliver? That's whack? That's your because here, because it's whack. I put the one on the side, I called that the top, and the one on the other side, that the bottom. Because it doesn't make any sense, because there is no top and bottom to this can.
Oh, okay. I see.
So is it really whack, Oliver?
Longer.
Is that really the word to use here?
It's more sensical and interesting than it is whack.
Okay.
Yeah.
I was about to flip out. I mean, because I could, I guess, if it makes you feel better. Does that satisfy your sensibilities better?
I see it now.
All right. All jokes aside, is that cool though? You all right? Hate for it to be too whack. It doesn't matter. We're gonna throw these away. Right? Top and bottom of the can has no flux passing through it. We expect the electric field to be perpendicular to the core of the wire. And so if we center our can, we know that we should have no electric field passing through the top and bottom. All the electric field passes through the sides. Still okay? So that means if we, again, big assumptions, bless you, that the electric field is the same value everywhere along the outside edge of the sides of our can, because it's equidistant from the inner core, then we can pull the electric field out of our integral. Let me get all this out of the way. There we go. So my goal is to say this is E, and sum up the area of the sides of my my cylinder. On the left side, enclosed charge, I'm going to have to put something here. I know that the charge density is the total charge over the total length. All right, that's got to be the charge density for the whole thing. I can use a linear charge density, even though it's a solid piece of core wire. Makes sense to do so. It's a linear density. But I also know that that means the Q enclosed over the height of my can. I know height's the wrong word here, but that's one I'm going to use. That ratio has to be preserved for the linear density to be the same everywhere. So that gives me something I can use for my enclosed charge in terms of the structure that I have. This is how you work charge into the problem. So I'm going to have QH over L as my enclosed charge on the left. Now, work out the area. It's the area of the side of the can. 2 pi R times H. Again, we've done this before. This is just the circumference of the can times the height. That gives me the area of the outside edge of the can. Am I good to keep going? Making sure I'm collecting everybody. All right. Solve that for the electric field. And you have successfully done step 2, which is use Gauss's law to figure out what the electric field is in the region of space that matters between the two charged plates. So E is going to equal, it's a little bit messy, but not terrible, QH over 2 pi epsilon naught LRH. It's messy, but not terrible. The H's cancel, as we would expect. The Gaussian surface structure shouldn't remain. The only part that we should see are remnants of the shape, in this case, the 2 pi. Q over L is the linear density, so it should match up with what we expect for a long line of charge, and it does. And that's what the Q over L is. So we kind of expect, we kind of know what it should be. That's why I'm telling you it's worth it to memorize the 3 basic structures: a sheet, a line, and a point charge. Either way, we now have an expression for the electric field in terms of the charge that's on the inner plate. Notice the outer plate didn't matter. Our next step, electric potential. This one's going to be tougher because, well, quite frankly, you've got more integration work to do. But I want you to see something, so we'll take a quick break for you to take out your equation sheets. Our job now is to take this and find the potential difference from the inner plate to the outer plate. You have to know a lot to do this. Part of it's just plugging in. So whatever expression you got for your electric field, you use it here. Q over 2 pi epsilon naught L R dr. Yes, sir.
Why don't you double it?
Why would I double it?
Because you have an electric field from the outside cable.
Do I?
Well, it's charged.
That means that this integral is Q over 2 pi epsilon naught L natural log of R evaluated from A to B. And I'm so frustrated we didn't finish this because we had to get on that long run. So look, you need to do this. And I'm afraid that you guys don't have a skill set that is required for this. And I'm not talking about the integral. The integral's done. I'm talking about this. You need to combine this better than what you have here, and there is a way, and you should know what it is. I don't know if you remember or not, and I know some of you have to go, but I don't care. You should know that rule. Now, I would like it very much if tomorrow when I come into class, I say, show me what the capacitance is here. And you should be able to show me that you finished this. And you should get a solid start on the one for the spherical capacitor, because it's easier than this one. Do I? If my red surface is my Gaussian surface and the green surface is the outer core of the wire that's negatively charged, what's my electric field due to the outer core of the wire? So do I double it?
Well,
No, well. It's a yes or no question.
I understand Gauss's law.
Clearly not.
So, well, from that point of view, no, but...
That's the only point of view that matters.
There's still going to be an electric field.
No, there's not. There's going to be electric field only from the inner portion of the wire. This does not create an electric field inside the wire or inside the shell even. You'd be the first one to say Faraday cage because you love bringing in terminology that you haven't learned yet. Cocking your head to the side like, trying to look cute, it's not helping here. What do you want to know here? All right, we'll pause. If we look at that point on Gauss's surface, inside a hollow shell of charge that has an unbalanced charge on the outside, you think there should be an electric field at that point where the X is?
I mean...
I was trying to gauge what you want, what you know.
When you just have an outer shell with nothing inside of it, it makes more sense because you have electric fields and they have no place to terminate or go, so they crash into each other. This is how I'm seeing it. But when you have a positive charge, you have a starting point and an ending point for the electric fields to go. So it doesn't make any sense why that wouldn't happen.
So you're saying that if I place the charge in here, the positive charge wire in here, like so, that will create an electric field in this region of space where the red circle is.
But I feel like that electric field should have contributions from both parts.
I'm sorry you think that.
Because, I think the issue is visualizing it. But because you would have electric fields that gravitate.